Thank you, Kevin. We'll start with what is renewable energy, and I will also preface this by saying this conversation is really about renewable energy upgrades to residences and other small structures. So we're not talking about institutions, we're not talking about church complexes, for instance. We're talking about 2,000, 4,000 square foot houses, office spaces, as well as existing buildings. I think a lot of what we're going to talk about today is about the trials and tribulations of working with renewable energy in houses that are sometimes 200 or 100 years old. But renewable energy from that vantage point is really about geothermal, which comes in all kinds of different stripes and creeds. What you see there is a coiled loop process and shallow loops on the left. There's also wind energy that can be harvested from rooftops or as independent structures. They can take the form of propeller-driven turbines to vertical axis turbines. And solar can happen through photovoltaics, which create electricity, or water heating, so solar hot water heating, which can not just heat up hot water for showers and things, but also for radiant floor heating and others. We're going to stick to what we've learned here, because I think the name of the game is what is it that we have learned in our process that we have just gotten through here in the last few weeks, actually, in many of these processes, and be able to tell you with honesty what we've been through here. So I think it really matters as to what kind of energy systems did you already have in your house and your office, what kind of utility options have been used there. So for instance, here, thank you, here at the Pennypack Trust, we're dealing with the retrofit of 3 different structures: an office, our visitor center, and what is now the executive director's house. And with regard to the visitor center and the executive director's house, heating was done with propane and cooling was done with electric. And the air handlers were a dual fuel system, so that forced air was happening with heating through propane and cooling through the use of electric and compressors. So having those utilities already in your building is important. You may also be currently heating with propane or gas, and you may be interested in using those as an alternative energy source or as a secondary energy source, particularly for heating and cooling. We'll talk about that later. But if you're really interested in making these conversions specifically for your carbon footprint and addressing issues of climate change, then a good rule of thumb is try to avoid combustion. Combustion denotes that you're going to use natural gas or propane or heating oil, and those things, you're basically chugging millions of years worth of distilled biological activity to heat and cool your house. That's not very sustainable. So if you can avoid combustion, please do so. And that leads us to the choices that we made here in our energy retrofits at PERT. First and foremost, we used solar electric generation through the use of photovoltaics mounted on the visitor center. And you can see that in the rendering that we made back in 2021. And use geothermal heating and cooling in all 3 buildings. So I mentioned that the visitor center and the executive director's house use propane and electric for heating and cooling. The office used electric for both heating and cooling. I also wanted to make sure that demonstration was going to be an element here in these retrofits so that we could walk people around to these areas, point to them, and show folks just like you who might be curious in how these systems are configured. What does it look like in our basements, in our attics? So if you're interested, please don't be afraid to knock on our door. Have anything to add in terms of context here, or the bigger decisions so far? Okay, we're going to keep on going. We're going to stick with solar first. I've got about 7 or 8 slides about what it's been like to put solar photovoltaic panels on our rooftop. We're going to talk about the return on investment and how we calculated the return on investment. Then we're going to stop that conversation and start with geothermal. Okay, they're isolated in this presentation. So what kind of options do you have in front of you for solar panels? First of all, as we said, we went with photovoltaic arrays, which means these panels are taking sunlight and converting them to electricity. Specifically, direct current electricity passes through an inverter where it's turned into alternate current electricity that most of us use in our houses and other structures. You can have those arrays mounted to your building roof, or you can also have them ground mounted in an independent structure out in your landscape, usually the backyard and not the front yard. When it comes to storage when it comes to processing the electricity that you're producing, you really have 2 options. You can feed the grid, which is a technique called net metering, or you can have on-site storage, which means that you're into batteries, and you have some element of self-reliance when you have on-site storage. We opted to feed the grid in what's called net metering, which means when we're not consuming a huge amount of electricity during the day, then those solar panels are producing electricity and putting it back onto the grid. With the models that the contractors provided for us basically say that despite what we're producing, we're going to be, despite what we're consuming, we're going to be producing about 45 to 55% of that consumption and pushing it back onto the grid. So feeding the grid is the strategy that we went with, along with roof-mounted arrays. We did that because we didn't want to junk up the space of the headquarters. And it's also some protection on a good solid roof that's only 10 years old. So you do need to make a decision about the quality of your roof and whether or not you want to put photovoltaics that could last 30 to 50 years on a roof that might not make it that far. So very quickly, I'll say in this process that contractors are a huge help to making these decisions. In fact, you really can't make these decisions without their help and without their assessment. So for our purposes, we chose 2 contractors to bid against one another. Both of them are local, and both of them produce or wrap solar panels that are made in America or made in a combination of the United States and Canada. That was important to me, it was important to the committee. So we used Evoque and Belmont. They both came back with phenomenal bid packages. And here's an example from Belmont that showed the photovoltaic arrays on the rooftop itself. They tell you about how much energy that's producing and what % of the current utility bill that might be offsetting. They tell you exactly what panels they're suggesting for this application and some of the technical aspects of what kind of solar aspect they're pulling from. I'll show you more later on, but they do recommend panel types. You have to get into this with contractors because they have relationships to buy those panels. And it's from there that they will estimate yield and total cost. The other thing I noticed about these contractors is that they're pretty much all inclusive. I didn't have to buy another contractor's services to get these things mounted or to get them plugged in. So it was essentially a plug and play model with these contractors. What we did have to have in terms of homework to get the solar arrays or to start contracting is that we did need to know something about the aspect of these rooftops. If I only had north-facing rooftops, I wouldn't be exploring putting arrays there. In this case, the visitor center or the majority of the visitor center rooftop was facing southeast, which is a pretty good aspect for solar gain in the morning through the mid-afternoon. We also knew that there wasn't going to be huge obstruction from trees nearby. maybe most importantly, there weren't trees that would shed limbs and potentially destroy those cells if a tree happened to fall on the roof. We also knew, as I said before, that the roof condition was really pretty good. So we were A-okay for mounting those things on the rooftop. And we had a good sense of how to connect back to our primary meter. We will show you examples of what that means in just a second, but that's part of the homework you should do. If you have a complicated route from where you want to generate electricity to where your meter is, that's complicated by structures or other utilities, then you need to plan that out well in advance. You also need to have a record of your recent electrical consumption. So at least 12 months, I would recommend. If you can get 24 months, that would be better. You'll see examples of the variability that we get between multiple years and why that might be important. So there's a certain point at which you cannot go forward without your contractor's help and without your contractor's bid. In this case, the bidders are telling you what your electrical yield is going to be off those panels. That's a product of understanding the efficiency of those panels. By the way, the most efficient domestically made panels with good warranties, we're getting about 22 to 24% efficiency out of each panel. That's per area. Only once you have those two figures can you estimate a return on investment, which is a measure of efficient, or it can be equated through efficiency of the panels, the amount of yield, and what your record is of consumption. And from that point, the contractor can estimate what your SRECs will be. These are credits or for the amount of electricity that you're selling back to the grid. So you do get revenue out of these things, but oftentimes that revenue, at least in this case, is simply offsetting electrical cost. Finally, I don't want to scare any of you, but I think it's really worth noting that based on where you are, based on the condition of your grid, PECO, our electric provider, could potentially veto the ability for your contractor or for you to connect solar photovoltaics to the grid. They say that that's rare. It was not a problem for us, and we have a fairly limited bandwidth for electricity here at the Trust. So we haven't had a problem with that, but I think it's worth noting that there have been instances where PECO can say, no, we're not ready to accept energy production on this portion of the grid. So what we learned from this process, installation happened in July, and I'm going to show you some pictures of what installation looked like this year. It was really so easy and so slick. We should have done more, although technically we could not have done larger arrays on the visitor center. We could have done more if we had decided to place that array, for instance, on our equipment barn off of Paper Mill Road. We also learned that we have pretty limited electrical capacity just based off our position on the grid and the fact that we have a limited trend that PECO has placed on the site. I don't know how many decades ago, but we have 200 amp service to all of headquarters, which most houses these days have a base service of 200 amps. We're running 3 different structures off of that. And if you count the greenhouses and the unoccupied structures, it's even more. Make sure that you have that uninterrupted, unfettered home run from the panels to the house. In fact, this picture shows that the panels are mounted to the visitor center just beyond that spruce there. And then that mound of dirt represents the new trenching for the cables that go underground and into the office and then to the meter. So you need to make sure that you are conflict free in that space, both underground and on the surface. Also, the contractor is going to install automatic disconnects. This is really important and has been an eye-opener for me. And that, let's say, for instance, the grid goes down for a day or two because there's been a winter storm, or there's been a windstorm and trees have knocked down power lines all over the grid. It's really important that guys can get onto that grid system and start repairing those things with confidence that there's not electricity in those lines. What we don't want is for home generators and home solar photovoltaic systems to be adding amperage or voltage to those lines and for them not to anticipate it. So there are automatic disconnects that make sure that A, your generator can come on and it's not complicated by solar yield. And also solar is not backfilling the grid and potentially being a danger to people working on those lines. So that's an interesting thing. If you're reading between the lines there, no pun intended, you're not going to get solar power off of your photovoltaics during an outage. The system will be down. So you will need to have some kind of backup solution if that's a concern for you. Finally, PECO has suffered from what do you call it? From product disruptions in production, supply chain disruptions. That's the phrase I'm looking for. And so they've not been able to source meters that can run back and forth. In fact, we have not yet had our backwards running meter installed. And as I said, these panels were up and ready to go by mid-July. We hope to have it up any minute now, any day now. We are completely ready for that, but PECO has not been ready for that. Drew, any comments or color commentary on solar? Because this, other than that, we've just got a few pictures to go through with regard to what that installation looked like.
Yeah, no, I think you've covered it really well. And I think the only comment I would add is that PECO's rejection is if you were to backfeed the grid. If you were to put your own battery supplies in at your home and just maintain your own system, they won't have any conflict with that. And you would have some emergency power in the event of an outage, but it would be limited because of the battery sizes. But other than that, went well.
Okay. What kind of, just to bring your credibility up here on solar, what kind of solar have you installed, or you and your contractors installed recently?
We haven't done anything in the historic district because the amount we would need to put in acres to put a dent in those bills. And it just hasn't come up. I've been involved in some smaller residential systems and, you know, but the big solar stuff, I'd love to get involved in. We just haven't ever, the school doesn't seem to have been interested in it yet for whatever reason.
It is really well suited for small scale residential.
Yeah.
So I just want to run through some pictures here. In mid-July, Evoque Solar just descended on us en masse with these 3 trucks, as well as the boss, actually the owner of the company, was there present. And they worked like busy bees all over the building. Just in a matter of 2 days, they had everything erected, including the mounting hardware directly onto the rooftop. And then it was another day in order for the conduit laying and for trenching to happen and to pull that conduit, make connections to the meter, and make expansion capacity at the meter so that PECO could ultimately put in their dual flow meters onto our main building. So this was really very painless. We didn't really suffer too much in terms of outage when they were doing construction. They weren't necessarily loud. This was really incredibly easy. So again, there again is the trenching. For those of you concerned about landscape, you know, I'm concerned about the amount of disruption that happened for the root system of those spruces and the sycamore, but I also know what those trees have been through over the years in terms of other utilities moving similarly through the landscape underground. So they've handled it quite well. Now let's talk about costs very quickly. And And before we just go rocketing down into the details of how much this costs and what is the real return on this investment, I think it's really important to make sure that, you know, we're talking about the big picture here. We are generating renewable energy, not just for us, but for the grid. So we're helping others become more renewable, greener, as it were. There is a neighborhood, indeed a global benefit to doing so. And one of the reasons why we were pretty dogmatic about using American parts and American panels is because we want to make sure that North America is working towards a greener, more sustainable industrial complex to provide this for us and for us to be able to get parts over the next 10 to 20 to 30 years. Hopefully the next time we buy solar panels, they'll have efficiencies closer to 50 or 60%. And we'll be able to get a whole lot more energy out of the same square footage as we did in 2022. But let's get into the numbers here. So our total annual electric bill was just a little bit under $10,000 for the 3 buildings that we're talking about. The total installation cost was just a little bit under $46,000. And we anticipate to get $530 a year in SRECs. In other words, that's how much the utility will pay us for the electricity that we generate. So most of the savings calculated in this return on investment is not in terms of the cost of electricity that we're generating, it's the cost that we're offsetting, or it's the amount that we're no longer consuming. So, so again, we produced almost $10,000 worth of electricity. We will offset, as you see here in the 2023 model, about a quarter of that, and then be reimbursed $530 on top of that. So our total expenses are going to be reduced by $3,000 or $3,200 a year, including the SRECs. When you combine that with geothermal, things are likely to get better. But when we look at the 2023 assessment here, devoid of geothermal, the return on investment is going to be about 14 to 15 years. When you combine that with geothermal, where we're no longer using electricity for cooling, but we're going to be using geothermal instead with some electricity to augment the pumps, to run the pumps and to run the air handlers, we expect that price to come down. We expect the amount of electricity to come down, and that brings our return on investment to about 9 years. Now, what I haven't talked about and what the contractors talk about in their bid is how much tax credit comes with this. We are a nonprofit, and therefore we don't pay taxes. Therefore, we don't get a cut of a tax credit for doing this. So there is a federal tax credit, as you can see highlighted in red, that will shave off almost 25% of the total construction cost. So this was the bid that they gave us. The actual construction cost was slightly lower than this, but you can see they have a very different way of explaining return on investment. So for those of you at home paying taxes, this could really pay for itself in well under 10 years. And I love the long-term thinking that's shown here in the estimate power and SREC production, in that it's saying over 30 years, you will save almost $120,000 for the same size array. And they have gone through the escalation of electricity rates at 3% per year, which is not something that I did in that return on investment that I showed you in the previous slide. So solar really makes a lot of sense. And I frankly, if there's questions out there about whether the new sustainable energy rebate programs are in effect here, they're not modeled here. So we haven't looked into what that new legislation could offer us, and indeed whether or not we'd be eligible, because this happened before that legislation passed. I do want to put a challenge out there to you guys, to the broader community. We don't know exactly what this ROI is going to be like. We're speculative on that. We don't know what kind of maintenance we're going to encounter over the next year or 20 years. And so we don't know how to model that cost. But I know that many of you are either thinking about going down this road or have already gone down this road. And I think it would be great if we could get together and we could share our stories and make a presentation like this even stronger by combining our stories together. So if you're interested in us your story, or if you're interested in telling us about your experience as you do this in the near future, let's talk. And let's see if we can't get more of our neighbors and friends to think about this as a result, because we can only grow our credibility by broadening our depth and our experience here. So let's move on to geothermal. Geothermal is certainly our biggest investment in renewable energy here. What we're talking about is a closed loop geothermal heating and cooling system. What you see in this diagram is the executive director's house depicted on the right, the visitor center on the left, the landscape that has not yet been constructed in between. And you see the well field basically in the front yard of the house. You'll see that exhibited in pictures in just a minute. So what is a closed loop geothermal heating system? What are its components? Each of those red rods that you see on the diagram represent at least 380 feet of vertical well. The well heads don't start until 4 feet below finished grade, so they're well under frost depth. And then they proceed another 300 to 400 feet below that. In fact, the two on the left that feed the visitor center are each 400 feet. These are closed pipe loops filled with water and added, there's a little bit of glycol added in there. And Drew has a note to say about that in just a second. But essentially, well, I'll show you a picture. It's a pipe that's about maybe 3 inches or less in diameter, and it goes down 380 feet to exchange heat with the earth, and it comes back up 380 feet to exchange heat. So we're talking about, what is that, 740 to 800 linear feet of heat exchange through those wells that's then brought back into the structure that you're trying to condition. We are mining essentially 58 degrees steady temperatures in the earth that are present below, essentially below like 20 feet below grade. So there's a lot of consistency in the heat of rock and soil and aquifers that are being mined here to bring the steady state temperature of these buildings to about 58 degrees. Then you use electricity and modern heat pumps to augment that. So clearly you could cool a house that might be running 85 degrees in July and bring it down to closer to 58 degrees because of the heat exchange. But when you're trying to heat a house above 58 degrees, you do need to add electricity. And here's where the science of heat pumps really gets beyond me. So Drew, can you help us on that?
I think a little bit. So basically, for people that are familiar with heat pumps currently are about the most efficient form of heating and cooling that we have. Their Achilles heel is that typically when ambient air temperatures get very low, they become very inefficient or go off completely and are not operable. In the last few years, that's actually gotten better. Heat pumps can run down to almost 0 degrees ambient air. But the sweet spot for a heat pump, where they're most efficient, where the compressor is its happiest, is right in that high 40s, low 50s, maybe to the high 50s range. There's about a 10 or 15 degree spread in there. And by keeping the heat pump in that range, you're keeping the heat pump at its most efficient. So in essence, it thinks it's 58 degrees outside when it's 100 degrees outside, or it thinks it's 58 degrees outside when it's 0 outside. And that's why the ground coupled systems are so efficient. And in a very crude way, if you envision a window unit air conditioner blowing cold air into your house, and you go on the outside of the house and it's blowing hot air, A heat pump basically has reversing components in it that change that so that it would be like taking that window unit out and reversing it in the winter time. So it would be blowing cold air outside and warm air inside. That's really what's happening in a heat pump. And so they reverse their cycle and they get the hot air in the interior in the winter and the cool air in the summer. And by keeping the heat pump in that sweet spot of the 58 degrees plus or minus, the unit is running at its absolute optimum. It's very interesting. Just in the last 2 weeks, BlackRock Investment has just bought a major component out of Emerson Electric. And one of the large components in Emerson Electric is a division called Copeland Compressor. Copeland makes compressors for refrigeration, heat pumps, heating and cooling for everybody in the country. And whether you buy a Carrier or a Trane or a Goodman or a Rheem air conditioning or heat pump system, 9 out of 10 times it probably has a Copeland compressor in it. And right now, heat pumps are getting very difficult to buy because of their efficiencies. So that's why we're heading in that direction. And that's why 10 years ago, we put them in the Bryn Athyn Cathedral and connected them to a 50 well, 500-foot deep system. And that church is running, about 90+ % of the time off the geothermal. And in extremely cold conditions, we're burning natural gas to offset. Currently, right now, the Glencairn Museum has a 27 well system installed under one of our parking lots, and that'll be feeding a fairly large component of the new heating and cooling system that this year and next year is going into Glencairn for the first time since the building was built.
Thank you very much, Drew. That's excellent. And you touched on something that I failed to bring up earlier. In the third slide here, we talked about what is your legacy system. And if you have a house, say in the 1950s, that's running on electric heat and electric cooling, maybe the most efficient thing you can do is to upgrade your heat pump rather than immediately go jumping into geothermal.
Yeah, if your heat pump in your center, if you have a heat pump in your house and it's more than about 15 years old, it may be worth upgrading at this point.
Thanks very much for that. Drew is also touching on some of the idiosyncrasies of geothermal that we're learning here at the Trust, which is it's important that you try and keep the geothermal system running in its comfort zone. So to have a house, if you have a house, for instance, you'd like to keep that geothermal system running at say 64 to 66 degrees, and you don't want to bump the heating up more than 3 degrees at a time, because when you exceed the ability of the pumps to extract heat or to produce heat, then you add electricity to make up the difference, and that just becomes an electricity burden. Drew, do you have a better way of expressing that?
Yeah, and typically, Chris, right now, like your geothermal pumps that you've put in don't have any electric resistance backup in them, whereas older units would have had those. But you do like to keep the buildings within a few degrees of that sweet spot. Turning them down 10 degrees at night is really not yielding you anything, because the amount of time it'll take to bring them back up, you'll just end up with more complaints. So like in the Bryn Athyn Cathedral, we occupy the building at 7 a.m. and we go unoccupied about 9 p.m. 7 days a week. And that's where they're happiest.
Thank you. So let's move on now to the next slide. Decisions for geothermal systems. It's possible to use electricity as a heating backup. It's also possible to use propane as a heating backup. However, you will always need electricity to move the pumps and to move the air handlers around. So just something to be aware of as you go through the design decisions with your contractor. Also, the location of the pumps is important. Where in your house can you afford to put them? Where is the well field going to be? And that has a lot to do with the amount of disturbance that you can take and how these trucks and other equipment can access your site. If you're trying to retrofit a house, that's particularly important. New construction, it might not be nearly as important because the whole site is a construction site in many cases. Whether or not you're going to use forced air or radiant heating, that all has implications to the technology that you use and where the heat exchangers go. Fit into a closet as they would in a condo. Are they going to happen in the attic? What are they replacing? Are they larger than or smaller than what they're replacing? And what is your backup generator capacity? Here at the Pennypack Trust, we both work and live at the trust. And so having a backup generator is important to keep employees working, to keep servers up and things like that, but also to keep families happy because they're here 7 days a week. So having a generator that can bring the geothermal pumps and heat exchangers on was very important for us. We don't want the electric grid to go down and for the pumps to go off because the electricity is out. So what was this experience like for us? Well, it started with drill rigs. And there we have the drill rig. I think that's on opening day, 66,000 pounds on a yard. And it hums along like a commuter jet, basically, for most of the day. It uses lots of water, huge amounts of noise, and lots of landscape upheaval. This is just the amount of kick that's generated from the first well that was bored here. And you can see that's straight out our front door. And there's the pipes. One of the pipe, one's headed down, one's headed back. Once you bore 6 or 7 of these wells, then you have an awful lot of mess on your hands, and it's all contained within fabric. And they did a very good job of keeping the mess contained, but you've got to be aware that this is going to be an eyesore for you and also for your neighbors for quite some time. Our landscape looked like this for a good 3 to 4 months. Drew, I'd love for you to talk about the science of geothermal wells and particularly the slurry of thermal grout and the use of glycol.
Yeah, so when you are drilling like any well, if you've had a water well drilled or anything like that, there is all the spoils that come out of the well. And when you're doing this and then you're doing it multiple times, it just gets multiplied. We had a lot more ground at the Bryn Athyn Cathedral, so we were able to build a detention area to capture all of that. And it was a lot easier. Chris's location was a lot tighter. And so it made it a little more challenging for them. Once they drop those PVC pipes down, and by the way, those PVC pipes are manufactured at the proper length with the U-bend in them, and then they're pressurized so that before you put them in whether or not they fail by checking them. They drop those down in, and then they fill the rest of the well with a grout. And it's basically like cementing everything together because you want the contact between the piping and the well wall, the ground, to be absolutely as tight as possible because air is insulation and you don't want that down there. So they will then re-grout those pipes, and they typically cut them off about 4 feet below grade, below the frost line, and then run them whatever the configuration is needed into the buildings and then back out. And then the other reason that we use a glycol mix, and some systems use them, some systems don't. The Bryn Athyn Cathedral uses glycol because we don't have generation capacity large enough to run our heating system if we had a sustained power outage. We have a generator that'll run the rest of the building, but not the HVAC. And so to protect that system, we opted to go to glycol to prevent it from freezing if it ever got to that point. Chances of that are pretty low, but that's why we did it. Now, glycol is not as efficient as water in conducting and transferring energy. water is the best, so you lose some of your efficiency with glycol. So the engineering that has to be done prior to the geothermal going in has to calculate all those things in. You just can't throw these things in as you go. By the way, on the side of that, about 90% of the geothermal or ground coupled systems that fail or do not work were poorly engineered. It's usually directly related to they just didn't do their homework and they didn't do it well. So getting a contractor that is very familiar with this, if it's a residential system or if it's a larger system, having an engineering firm get involved to do the math is very critical.
Very much true. So if you're doing a retrofit, if you're going to retrofit a house with geothermal, we had quite a bit of clearing out to do. So this house, the executive director's house, has is built in 3 segments, one in the 1900s, one in the 1800s, and one in the 1700s. And we have a huge amount of legacy infrastructure through the house, much of which was a liability. So what you're looking at here is the #1 fuel oil tank. That's the reservoir for the #1 fuel oil furnace that you see on the right, painted in white. The center furnace was a coal burning, actually a dual fuel coal and wood burning furnace. And then off the picture are another 2 coal furnaces that heated this house, probably from a 1925 retrofit. There was asbestos covering most of that. There was lead paint on some of it, but most importantly, there were 4 types of asbestos that were part of this whole system because it was key to heat or to insulation as well as fireproofing. So we had a lot of infrastructure to haul out of the house. We also had to expand our electrical panel for more breakers because, as I said before, you do need electricity, about 60 amps worth of electricity to power your pumps. You know, to be honest with you, we were also updating the septic system here in the house, which also required more breakers. So it wasn't necessarily just geothermal that was requiring more bandwidth per se in the breakers, in the panel boxes, but it was about time that we updated those. We also had to upgrade our generator. We had an old generator, about 6 years old, that was only keeping part of the house electrified during storms, and it kept one of the heat exchangers on so that we could stay warm in at least part of the house. These days, generators are much more efficient and less costly, so we were able to get a whole house generator that can be programmed to on the pumps in sequence, which have a big amperage demand when they're turned on. We also, and if you're going to do this again as a retrofit, the amount of laydown space for equipment, the amount of laydown space for the heavy equipment that's doing the drilling and the earth moving is something to be reckoned with. So be aware that there's going to be your new systems in boxes, your old systems are going to get torn out and put somewhere. There's going to be vehicles at various places, and it's going to feel like a construction site. In our case, it felt like a construction site. It was a construction site for 6 full months. Now, geothermal is under a lot of demand right now, and contractors are spread thin. It's also a difficult environment for hiring and for training. So I hope your experience will be less than the 6 months that we went through. And we also, unlike the solar panel experience, we had to coordinate between the geothermal folks and our electrical contractor. So the geothermal contractors were not about to build us new electrical panels and give us new conduit routing to new locations. That was something that had to be contracted through our local electrical contractor. Here's a look, by the way, of our existing electrical panel. Before we started this, both of those panels, even though the doors are closed, were full. The generator panel below it And then afterwards, RNK, Rob Keyes Electric, by far and away one of the best contractor I have ever worked with is Rob Keyes, based out of Bryn Athyn. He did a brilliant job of updating our electrical systems here. And you can see lots of space still being created in the panel on the left. The same thing was happened at our office as well. But can't overemphasize the amount of disturbance happening to landscape and to site work. In Drew's case, and what I've seen in other institutions like high schools and institutions of higher ed, you can put your well field under a parking lot, and you can patch up that disturbance, and you can move men and equipment over those landscapes with very little problem. But in this case, we're doing it in a front yard, which was the only available option we had to us. Maybe your case as well, if you don't have a parking lot, and I'm pretty sure you don't. Other things of note with regard to disturbance in historic buildings, the mortar in a foundation that's 200 years old is gone. And so punching through a foundation wall with new line sets means that you also have to repair that wall when you're done punching through it, because it could just very well fall apart. That's a process that's still ongoing here. You can also see how deep down those line sets are going. That line set that you see on the left is headed out from the well field and into the visitor center. But in the end, you do save an awful lot of space. These are the pumps that are pulling water in and out of the earth into that well field. And we have an awful lot of functional basement left. And we've gotten rid of all the liabilities of the asbestos and the coal furnaces and the weird pumps and plumbing that you just don't want to have sit around much longer, particularly when it's charged with #1 fuel oil or something like that, or caked in friable asbestos. So the same thing is true here as we examine costs and the return on investment. This has a lot more to do with where we're going as a country and as a planet than it does in the details of the numbers, but we'll get to the details and numbers in just a second. I would recommend at this point, having seen the level of disturbance that we've just been through, that this is going to be so much easier in a new build than it will be in trying to retrofit an existing house, particularly an existing house on a tight site. You may, however, if you're flipping a house or if you've just bought a fixer-upper, this could be the catalyst for all kinds of systematic changes throughout the house. So if you have an electric heating system that's 15 or 20 years old, now is the time to upgrade that. And you may want to think about switching to geothermal and doing the entire trick, as it were, because your infrastructure is at least 15 years old already. So what do the numbers look like? Geothermal installation cost, including extras, was $162,000. We spend roughly $8,000 to $9,000 on propane before this every year. However, the cost of propane was rising on us just in the 2 years of analysis that you see here in the table. So we were spending $4.80 on a gallon of propane in 2021. Basically, the cost went up for every individual delivery that we got through 2021 and 2020, such that at the end of the 2022 heating season, we were paying $660. A think tank by the name of NOMA projects that the cost of propane and LNG is likely to double over the next 20 years. So we projected that in our 2043 analysis here. And that basically on this is somewhere between 16 years as you increment between $6.60 a gallon to $13.12 a gallon in each of those years. That incrementally goes up in that 20-year period. Or it could be 23 years if you're simply talking about today's cost at today's construction value. Sorry, today's cost of propane at today's construction value, which I think we all know is an unrealistic scenario. If you bundle in the cost of all of the other things that we had to do here, and I'm talking about the Pennypack's experience in expanding electricity, getting rid of asbestos, selective demolition of all those furnaces, then you're talking about adding another $42,000 in that demo and other improvements. And that brings your return on investment out to at least 19 years or 30 years, again, depending on the unit of gas or the unit of propane that you're dealing with. But we expect these systems to last at least 50 years. I think that the well infrastructure in particular is going to last far beyond that. So changing out pumps, changing out heat exchangers, that's likely to continue to occur over the lifetime of these systems. And we hope that they get even more efficient than the ones that we see now. But it's, I think, with a heating system for a place that you're not leaving, right? Or a place where you can invest that money and then sell that to the person you're selling your house to, it's an achievable number to get a return on. Drew, do you have any comments about that?
Yeah, and when we did the Bryn Athyn Cathedral 10 years ago, we had a couple of unique situations. One is that putting equipment outside the building would have been very difficult there because the 360 degrees all the way around the building is landscaped and beautiful. So hiding something outside was difficult, and ground coupled heat pumps removes that headache. The other thing is that we're not getting rid of the building anytime soon. You know, homeowners typically are in a house 7 to 10 years on average. You know, we're here for the duration, and these improvements like the well fields, they'll last 50 plus 100 maybe years before any issues. Heat pumps can be replaced in location in the building and be reconnected to the loop. And, you know, you'll be doing that no matter what system you put in, whether it's gas or oil or electric or whatever. Parts fail, things have to be replaced. So you've always got those components. So we really looked at it as we weren't so concerned about the short-term payback. We were looking at the long-term payback. And we came to the same conclusion at Glencairn when we were doing the planning on that building. And that's why about 2/3 of that building is going to be ground coupled, and the other third is going to be a conventional system because of the space sizes. But other than that, we've been really happy with the results. The electric bills are very, very reasonable. We don't have issues, and we're not burning much fossil fuel.
Thank you for that, Drew. I want to end this presentation here. We're very close to the end, to talk about for a second, at this point, what would we do differently? There we go. There's the slide I'm looking for. What would we have done differently so far? And I think this really applies to most homeowners, is not just the Pennypack Trust. The ability to upgrade your buildings and think about infrastructure on an annual or semi-annual basis is really critical. To not do asbestos abatement, to not have to pull out 100 years worth of different types of furnaces would have saved us an awful lot of time and an awful lot of money. And not to mention the cost of doing that would have been much cheaper 50 years ago or 25 years ago or just 10 years ago than it was today. So keeping up on what your building needs to stay healthy and to stay nimble is important. And it will make these larger system changes a little bit easier on your wallet. I wish that we had engaged an MEP that is a mechanical, electrical, plumbing, engineering service to have thought about the two systems working together. So what were the efficiencies or inefficiencies that need to be thought of when solar and geothermal would be combined? I think we would have found out that we could have gotten an awful lot more bang for our buck in terms of solar deployment, if we had choose to spend most of our money down at the equipment barn on a much larger roof with much greater solar aspect through a much longer part of the day that is both east facing and west facing. And that could have offset a much larger amount of our electric footprint, both current and future. That would have changed our ROI. And it may have also changed the way in which we would have used geothermal. So if we weren't using propane in the office, for instance, maybe we could have just spent that money, the geothermal conversion money, onto more solar back in another location and saved a little bit of money on geothermal deployment only for the executive director house and the visitor center. So these things could have really helped if we had brought in an MEP to help us do that planning earlier. That would have tacked on, I think, easily another $20,000 worth of just assessment and professional services to do that. So it's by no means free, but it would have probably also changed the ROI. As I said, as I've said 3 or 4 times now, we would have gone bigger with solar. It was just so much easier, so much less disturbance. But that said, I'm glad that we have a diversified system. I know that we have a heating and cooling system now that will work whether or not the grid is working. And we have a backup system to make sure that that's the case. And I also know that we're not borrowing from a grid system that can change its carbon footprint from year to year based on global conditions or the planning conditions of PECO or others. Drew, do you have anything to say about that?
No, I don't think so.
Let's see. Again, I want to emphasize the community challenge here. If you're interested in doing a solar retrofit or a geothermal retrofit, please let us know. I think it would be great if we could bring our stories together, and as we bring that credibility together, we might get more and more people to join in this cause. And we just want to be of service to the neighborhood as they think about less carbon in their energy diet. So thanks very much. If you have any questions, you can reach me at cmendel@pennypacktrust.org, and you can also reach Drew Nehlig at anc-gc.org. Thanks very much. I will go to chat for questions. If you do have a question and you want to do it live, just raise your hand and I'd be happy to unmute you, get you on here.
There was a few in the chat box.
Thanks, Kat. So I see a comment from Mark Moombauer. Please consider adding your solar stats to pvoutput.org. We'd love to have your system on board. Thanks very much for that. We do need to get into multiple systems for monitoring the progress of the production of our solar panels, as well as to declare our SRECs on a monthly basis. So thanks for that input there. Jeremy Haymaker asks how much disturbance comes along with 380 feet worth of wells. I think that our photographs told no lies about how much disturbance was involved there. And Jeff Clark comments, so for the unfortunate souls who have too much shade for solar PV arrays, I suppose the best thing we can do for the environment, if geothermal is not also a possibility, is to move to electric-based power. I guess that means installing a heat pump. Right now we have forced air heat with natural gas and have central air for cooling. Seems a heat pump would be a big investment. I'd like to challenge Jeff on that and say, you already have a heat pump. And you, as Drew had mentioned before, if that heat pump is greater than 15 years old, you probably need to upgrade it. And that return on your investment is likely to be well under 20 years. Drew, do you have any comment there?
Yeah, without seeing his system, if he has central air, he's already got a component of it. And if both heating and cooling are using the same ducting system, which I'm guessing they are, you can replace your central air unit and your gas-fired or oil-fired furnace with a heat pump, and you should be fine. And if you buy a high enough SEER one, you should get down to that 0 temperature range. Now, some heat pump manufacturers also make what they call dual system that has a natural gas backup or a propane backup built into it that will kick on if you get too low. But without seeing it, I'm a little bit guessing in the dark, and getting a good contractor over there is critical.
Would you recommend having an engineer look at it before a contractor, or what do you think the average resident should do?
I think if they've got a good relationship with a good HVAC contractor, I would start there. You know, when you bring the engineering firms in, it gets very expensive very quickly, and typically homes don't really need that. They're not that complex.
Is there anybody you would like to plug around here locally who might be capable of doing that?
Typically, I don't like to plug anybody, because with the way the economy has been lately and these vendors are stressed out, somebody that gave one person a good reply and was very timely, they won't be timely to the next one. So, you know, if you want to email me on the side, I'd be happy to help. But if you have a good relationship with somebody currently, I would start there.
Well played, Drew. Well played. I don't see any other comments or questions in the chat. I don't see any hands raised. So I think it's time to wrap things up. I'll just make a last call. Anybody, any comments or questions here tonight? Kevin, are you seeing anything?
No, I think we're good.
Okay. Thank you all so much for your time. We really appreciate, first of all, that you've given to the Pennypack Trust to give us the opportunity to experiment with these things and for us to relay what we've learned back to you. We really hope that you try to do something to minimize your carbon footprint in the next couple of years. It really matters. Thanks so much and have a great night. Thank you, Drew, for helping me.
Great. You're welcome. Have a good evening.
All right. Take care, man.